Okay, our speaker today is Devarshi Mukherjee, and his title that you can see there is Analytic K-theory for bornological spaces. Please, Devarshi, go ahead.
Okay, thanks for the invitation. Um, okay, let me get to it. So I'll start with some motivation, which, at least for this talk, the motivation comes from invariants of, well, C-star algebras or bornological algebras, also in the non-archimedean setting. Okay, so let's see what happens for C-star algebras. At least for stable C-star algebras, the primary invariant is topological K-theory, and that's because by Hickson's result, we know that topological and algebraic K-theory are the same for up to stabilization of the C-star algebra. And well, there are many ways to think about this result, but one way is that algebraic K-theory, when applied to a C-star algebra, becomes both periodic automatically and homotopy invariant as well. So in a sense, it suffices to look at topological K-theory if you care about C-star algebras.
Let me interrupt you a second.
Yeah.
This result is due, as you wrote it, is not due to Hickson, but to, for negative n is due to Karoubi, and for positive n is due to Suslin and Boschisky. What Hickson proved referred to the Kalkin algebra. Stabilized using the Kalkin.
Right.
And require array to be unitary.
Right. What's the other name you mentioned? Suslin, yeah.
Suslin and Boschisky.
Yeah. Okay, so that's the result. And okay, so that's the K-theoretic side of things. And of course, that's hard to compute. So you compare it usually, well, upon rationalization, you compare it with some cyclic homology theory. So let's say periodic cyclic homology. But it turns out that periodic cyclic homology is not a good invariant for a number of reasons. Well, one reason is it's not homotopy invariant for continuous homotopies. Another reason is it is not invariant and passage to smooth subalgebras. I'll come to what that means in a second. And from the point of view of this talk, this is sort of the property I'd like to get into some depth with. Okay, well, what is...
I remark one more thing.
Yeah.
It's zero. In A, if you have a K-stable sister algebra and you apply HP of it, that's zero.
Yeah. No, yeah, well, I'm
So
just talking about
I'm
talking about the properties of this HP when applied to this category.
Yeah. What I mean is, if you apply it to a stable sister algebra, you get zero.
Right. Okay, so there are a number of reasons why you shouldn't use HP to approximate topological K-theory. And to kind of get around this, one defines another invariant, but it's not so easy to define. You need to enlarge the domain on which it's defined. So things like passage to smooth subalgebras and defining more refined invariants requires passing to a larger category. Okay, and I will not define what this refined invariant is, but if you've worked with invariants of C-star algebras, then you know what it is. But I'm mainly using it as a motivation to define analytic K-theory. Okay, so what is this larger category? We work with complete bornological algebras. And the invariant is analytic cyclic homology. And you map into the derived category of complete bornological spaces. Okay, and I also mentioned this passage to a smooth subalgebra. So what one does is we find a subcategory which is closed under holomorphic functional calculus. And well, this can be identified with inductive systems of Banach algebras. So these are just filtered unions of Banach algebras. I should put the word strict over here. Okay, and well, this is not yet complete because this invariant that I've defined, that is analytic cyclic homology, this is not invariant under passage to a smooth subalgebra. So in other words, if you start with some bornological algebra and you pass to this category, then in general, this depends on choices. Okay, so instead, how one resolves this is by defining another functor, which in a sense compactifies the bornology. And what that means is it equips the underlying bornological vector space with the bornology of compact subsets or pre-compact subsets. And it turns out that this composition, which I can redefine as local cyclic homology, this is invariant under passage to a smooth subalgebra. Okay, and well, how is this maybe defined? This is just HA of the pre-compact bornology on A. Okay. Let's maybe take some example of this entire process of taking a C-star algebra or some bornological algebra, passing to something smooth, and let's see what happens. Well, the prototypical example is, of course, you take a smooth manifold and take smooth functions on it. Now, this is contained in continuous functions, the C-star algebra of continuous functions. And if you then equip this with the pre-compact bornology, you still get a bornological embedding. And this is an equivalence once you apply local cyclic homology. Okay, and there's something similar which happens over ZP. Here again, what one does is we start with complete and torsion-free bornological ZP algebras, and one passes to dagger algebras. And again, does this recipe of applying the pre-compact bornology. And there is a derived category, analytic cyclic homology. And this composition is local cyclic homology. And this, well, this is, of course, also invariant under passage to smooth subalgebras, but there's also more that happens. This only depends on the reduction mod P. And well, and this really implies that HL of one of these smooth things is the same as HL of the p-adic completion. Okay, so why did I really mention all of this?
One
Yeah.
one question.
Yeah.
On the smooth things, does
Mhm.
HL agree with HP?
Not in general, no.
But in the complex, in the yes Archimedean case?
Also not. You need some finiteness, some homological finiteness assumptions. You need a projective dimension to be finite, and then these things are the same.
Okay,
Okay, so right, what is the kind of philosophy? At each instance, what we did is, well, we started with a, let's say, a complete bornological algebra or topological. That's the first thing we did. The second thing we did was we compactified it. That is, equip A with the pre-compact bornology. And well, what this does is this leads to somehow better finiteness properties. And that ultimately leads to good invariance. That is, if you finally define your invariant as some invariant which did not have these finiteness properties, but if you compactified it, then the resulting thing ends up having nice properties. Then you get an invariant which is homotopy invariant, stable, excisive, and invariant under passage to smooth subalgebras. Okay, so that's the story for topological or bornological algebras. The question I'd like to address is, well, first, how to categorify these invariants. Yeah. And more importantly, how to categorify this compactification condition. Okay, and well, before I kind of get to well answering these questions, let me say what happens purely algebraically. So purely algebraically, if you see where I started, that is with algebraic K-theory and periodic cyclic homology, these are not just invariants of rings, but also invariants of small stable infinity categories. And that's not just true for K-theory and periodic cyclic homology, but everything that's related to these invariants, such as cyclic homology and negative cyclic homology and Hochschild homology, THH, and so on. So these are not just invariants of rings, but also invariants of small stable infinity categories. And they map to, let's say, some stable infinity category, such as spectra. And well, these are not just invariants, but they also satisfy things. These are localizing invariants. That is, they satisfy or preserving fiber cofiber sequences. Okay, and well, if you don't know what these words mean, okay, small is just an infinity categorical analog of a category being locally small. But stable infinity category, well, one way to think about this is because we'll only care about Z linear things, then these are just the same as DG categories. So you can essentially think about whatever I'll say for now as small DG categories. Okay, right. So that's what happens algebraically. And of course, you recover these invariants by taking perfect complexes of a ring. Okay, right. And if you take this kind of as a definition of invariance of rings, then these kind of perfect complexes or stable infinity categories should be viewed as non-commutative spaces. So this is sort of the definition of a non-commutative space that shows up in Tabuada's papers, for instance. Okay, and well, why do I call these non-commutative spaces? You would ask what happens in the setting of algebraic geometry. So in algebraic geometry, you can recover a scheme, let's say, from its category of quasi-coherent sheaves, from its derived category of quasi-coherent sheaves. And this is, again, a stable infinity category. And it's also generated by, or rather, it's given by the int completion of its category of perfect complexes. And therefore, if you want to define invariance of schemes, that is, if you want to globalize these constructions, then you simply define the invariant of a scheme as E of perfect complexes of X. And of course, it is in this context that you need to show that this is well defined. That is, it does not matter how you globalize. So if you take different covers, then you still get the same thing. So implicitly in this, one shows that the invariants above satisfy descent. Okay, so this was all purely algebraically. So you take a scheme and you apply your invariant to the category of perfect complexes. Oh, so now the question is how to generalize this to, well, if you work with algebraic geometry, then complex or rigid analytic spaces. Or if you just care about rings, then bornological algebras. But again, just bootstrapping from the purely algebraic case, there's a common way to answer these. So that is, what is let's say an underlying category such that E of C would recover E of R. Okay. Okay, now let's see how to, first of all, go about finding such a category. So let me give a very short, well, let's say a few words about derived analytic geometry. Let me just put derived in parentheses, but it's part of the same story. So we start with some Banach field. Take its category of Banach spaces, and then build its category of inductive systems of Banach spaces. And inside this, there's the category of complete bornological spaces, which are the strict inductive systems of Banach spaces. And these categories, well, one should think of both these categories as if you were working with the category of abelian groups, because they are what are called elementary quasi-abelian categories. But this one is not exactly elementary, it's elementary from monomorphisms, but this one is an elementary category. But that doesn't matter because the derived categories are equivalent. And this is furthermore equivalent to the left part of this category, where this left heart is an actual Grothendieck abelian category. So in this sense, these categories are ideal to do some kind of homological or homotopical algebra, and that's ideal for algebraic geometry. Okay, so that's the category. What are the affine schemes? The affine schemes are just the commutative algebra objects inside the non-negatively graded chain complexes. So these are the affine schemes. And now to glue them, that is to prescribe some descent data, we define the following topology, where the covers are bornological algebra homomorphisms or homomorphisms of differential graded algebras or simplicially commutative algebras, which satisfy the following. They are idempotent over A. And they satisfy a certain transversality condition, which I won't get into right now. And this is really an analog of the Zariski topology. So it's also called the homotopy Zariski topology.
This is the same that was featured in what was it Federico's talk or Alex' talk?
Yeah, so that was, I think, for the in the non-commutative setting. This can also be defined for non-commutative algebras. Yeah. Yeah, so this condition is what Federico mentioned, I think. So these are called, this is another way of saying that the map from A to AI is a homotopy epimorphism. Okay. Okay, so these are the affines. How do we glue them? Well, okay, so these are the affines and this is the cover. Well, we glue them by simply taking sheaves for this site.
I think yeah, it should be the case that the collection of fallbacks is jointly conservative as well. Should be a cover.
Right, right. Yeah, I sort of subsumed all of that in this transversality condition. But yeah, that's true, that's true. So you need some.
I mean, the fact that the covers cannot depend on a condition over each eye, right?
Sure. Yeah. Okay, so then you just take sheaves for this site, and this gives you this category of bornological stacks. And in the case where K is the complex numbers or QP, then this contains analytic spaces in the classical sense, that is complex or rigid analytic spaces. These embed fully faithfully into the category of schemes. Okay, that's how you get schemes now, or that's how you glue rings together. How to glue modules? Okay, so you define this functor to the category of presentable stable categories whose morphisms are left adjoint functors. And this takes some spec of A to the derived category of A. And it's not so hard to check that this is a sheaf of infinity categories. And well, maybe I should just give a remark here. This is one.
Have you?
What's that?
You haven't defined spec A, have you?
Spec A is just the formal dual of the category of commutative algebras. So if I take a commutative ring and I just view it in its opposite category, I just call that spec A. This is not like the prime ideal spectrum or anything. I mean, I could just as easily, yeah, if I just take op here, then I can just say A goes to D of A. So the assignment which takes a ring to its derived category is a sheaf. Okay, and this is just false if you work with DG categories. Or, sorry, not DG categories, but the triangulated category of the derived category of modules. So you need some homotopy enriched notion for this to be true. So this is not true one categorically. I with as a triangulated category. Okay. Right, so that's how you glue modules together. Now coming back to the question, okay, now it makes sense for me to talk about the derived category of an analytic space. This is some presentable stable infinity category. This is actually also compactly generated, and this is equivalent to this original domain I had defined for localizing invariants, that is small stable infinity categories. So this is the same as in the notation used as this, is small stable infinity categories.
What is X in this assertion? Is it a sheaf?
X is an analytic
graph?
space. Yeah. So yeah, X is an analytic space, but X is a bornological scheme in general.
So, but as defined above these derived schemes, or
Yeah.
okay.
Yeah. Okay, so d of x belongs to this domain where I can apply things like K-theory. But unfortunately, it's not the right thing to plug in. Well, first of all, you have Eilenberg swindle because d of x has countable coproducts. So you cannot, you of course, even in the algebraic setting, you just cannot plug in d of x, you have to take its compact objects. Now, k of compact objects in this setting also has Eilenberg swindle. D of x compact is 0 by Eilenberg swindle. But there should be no hyphen here. So in other words, if you try the naive idea that you had, let's say, in the algebraic setting, that is, you take the derived category of a scheme and you define the K-theory of a scheme as K-theory of perfect complexes, where perfect complexes are the compact objects of the derived category of a scheme, then this does not work here because this has countable coproducts. Okay, so you need to do something more clever. So now again, just as in the
I think it doesn't quite have countable coproducts, but it has this like contracting subcategory.
right,
And
yeah,
that has
and then that
countable
also
coproducts,
suffices
yeah.
for Eilenberg swindle. Yeah. Yeah. Okay, so what you then do, just like for us, HP wasn't a good enough invariant, we had to refine it to HA. One needs to also refine K-theory in a suitable way. And again, the way to do that is by enlarging your domain from small stable infinity categories to large stable infinity categories. Okay, so solution, refine K-theory. And the precise way this is done is due to Efimov. So originally the localizing invariants were defined on this category of small stable infinity categories. To some stable infinity category. But Efimov's theorem is that any such invariant extends to the category of dualizable stable infinity categories. Okay, now I want to explain what these words mean in some sense, at least roughly. Okay, so this, if you take some small category, you can take its int completion, and that gives you a presentable, compactly generated stable infinity category. Now, what is such a category? So some category C is in this PRLCGST if every object can be written as a colimit of such a sequence. Where each of this is a compact object.
Is there the sequence
Mhm.
indexed
That
by
is
the
it.
natural numbers or some more later?
Okay, now an object is dualizable if you have something slightly more general than this. That is, if every object,
Sorry, could you briefly explain why small stable infinity categories are equivalent to PRLCGST?
so the functors in both directions are as follows. You take a small category, you take its int completion, and in the
Uh-huh.
other direction, you take a compactly generated category and you take its compact objects.
Oh, thank you.
Yeah.
So the
Okay,
functors in this category CG they're required to preserve compact objects. So it's like strongly continuous functors or something. So it's like sometimes it's called PRLL or
That's, I think, in the dualizable
oh,
case.
okay.
Yeah.
Yeah. Thank you.
Okay, so what is a dualizable category? So every object is a colimit of the following kind. Of compactly exhaustible objects. Okay, and what does that mean? Compactly exhaustible means that this is a colimit of things of this form. But these things are compact morphisms. What is a compact morphism? If for any z in C, where this morphism is in C, if for any colimit of objects in C, and G from Y to Z, we have the following. So this composition factorizes through some finite stage. That's what it means for a morphism to be compact. Okay, let's maybe take an example of a dualizable category. Let X be some locally compact Hausdorff space. Then one can talk about its sheaves taking values in spectra. then in this case, this compact exhaustion just means that, so U is compactly exhaustible in this categorical sense, if and only if U is if U is an increasing union of compact subsets where the structure maps in this inductive system are of the type where Ki is included in the interior of Ki plus 1. So that's what it means explicitly for something to be compactly exhaustible in this setting. So this is compactly exhaustible in the usual site of open subsets. And you can show, well, there are different ways to show that sheaves on X is dualizable, but one can just go through with the definitions and show this as you can take a sheaf and you can show that it's a colimit of sheaves which are defined on these kind of compactly exhaustible subsets. Okay, so that's an example of a dualizable category. In the first talk in this series, I think we had Bunke talk about E-theory. So that's another example from non-commutative geometry. E-theory is dualizable. So see Bunke. Okay. Right, so that's what a dualizable category is and some examples. Okay, maybe another source of examples comes from compactly generated. So all the previous examples that we knew of compactly generated presentable stable infinity categories. So let's say the derived category of a ring or the derived category of a scheme. These are for any compactly generated presentable stable infinity category is dualizable. Okay, so that's a bit on dualizable categories. And Efimov's theorem states that any localizing invariant of the previous world of small stable infinity categories extends to dualizable category. Okay, now the question is how to build dualizable categories. So just to kind of zoom out, what we're trying to do is we're trying to define certain invariants of either analytic spaces or bornological algebras or suitable categories which generalize these two, such that K-theory is non-trivial. That's what we're trying to do. So implicitly what we're trying to ask, what is the right dualizable category to plug in? So if you take just the derived category of an analytic space, and if you take its compact objects, then we know that K-theory vanishes. So we cannot simply work with small categories. So what is the right dualizable category to be working with? Okay, and here there's a theorem by Clausen, which goes as follows. There is a right adjoint functor from symmetric monoidal categories, symmetric monoidal presentable categories, that is commutative algebra objects in PRL to what are called rigid categories. So there is a right adjoint functor to the inclusion. Okay, let me now explain this a bit. And this is a certain subclass of PRL dual. So in other words, you take a symmetric monodal category, this construction will give you something in dualizable categories. Okay, and what is this functor, roughly speaking? It's a very technical result, so I won't get into too many details of that, but let me at least fix some notation. Okay, so what is this construction? This functor takes compact morphisms to trace class morphisms. Or let me put this more precisely. So to a category where compact morphisms are trace class morphisms. Okay, and why did I kind of give this introduction about this compactification in the operator algebra sense? And it's roughly because the same thing is going on, and I'll also make it precise, but before that, let me say in what sense it's the same thing. Wait. Okay, so over here, this functor, which took a bornological space and compactified it, this was also a right adjoint functor, and it mapped to, so let's say, analogy. Bornological spaces to compact bornological spaces. Okay, and well, what this compactification functor did was it took a bornological space and it spat, or it just equipped it with the pre-compact bornology. And this was a compact bornological space. And this was the universal way of doing it. That is, form in this category of compact bornological spaces from X to CPT Y is the same thing as home in bornological spaces from X to Y. And roughly, this is the same thing that's going on in this rigidification situation where we have, so categorically, you have home in rigid categories from C to D rigid is the same thing as home in, well, not categories, but PRL commutative algebras from C to D. And okay, the way we finally came up with these functors was by compact A, and that's how we defined HL of A. On this side, one might wonder what happens when you try to do something similar. So what happens if we take K of the rigidification of D of X? as the definition of K-theory. Or in terms of rings, so if you just care about bornological algebras, you can take the K-theory of A, and this is the continuous extension of K-theory in the sense of Efimov. So this is E continuous. Well, maybe let me define this K-theory. So the analytic K-theory of a bornological algebra is defined as the continuous K-theory of the rigidification of the derived category. And it turns out that this is the right way to go. So now, well, to justify that, let's take the case where K is QP. Then in this setting, if you take the rigidification, then what you get is the category of, well, it's the globalization of the category of nuclear modules. Okay, so that's Efimov K-theory applied to this setting. And now you might wonder what properties this K-theory has. And well, the first thing one should try to prove is descent properties. So let me now summarize the properties it has. So first of all, nuke satisfies Zariski descent. But also, well, I should say this is a theorem. Nuke also satisfies Nisnevich descent. And as a consequence of that, well, one can just literally take a look at Thomason-Trobaugh's paper, and whatever he uses to prove that K-theory defined via perfect complexes of a scheme satisfies Nisnevich descent, you can literally use the same arguments to prove that. So using Thomason-Trobaugh's proofs, I can prove that K-an satisfies Nisnevich descent. Okay, so that's these are the descent properties, and I'm running out of time, so I'll just say this in words. I mean, this we've kind of set it up in a way that we can prove things like Riemann-Roch theorems, which is really about the push-forward functoriality of nuke and then K-theory. But I'll spend the last 5 minutes to maybe further this analogy between what goes on in non-commutative geometry and in this kind of new Efimov K-theory setting. Okay, so right, so far I've been mainly speaking in analogies between this compactification of a bornological space and the rigidification of a category. What can we say that's slightly more precise? Okay, so this part of what I'm saying is work in progress with Thomas Nikolaus. If you take a bornological algebra first and you compactify it, this is just another bornological algebra, let's say complete and so on. You could then ask, what is the derived category of this algebra with the precompact bornology? it turns out, well, at least let's say in the non-Archimedean case, and I'm pretty sure about this. So over QP, this is precisely the rigidification of the derived category of the complete bornological algebra. And well, this is the first thing. The second thing is if you just start with a locally compact Hausdorff space, you could take its one-point compactification and you could equip this topological space with the bornology of pre-compact subsets. And this is, well, a bornological topological space. And now if you take sheaves of X, let's say with values in spectra, and if you rigidify this, then this part is still it's almost worked out, but we haven't fully written out all the details. But this should be the compactification with the pre-compact bornology. So in some sense, it's, well, not in some sense, but in a very precise sense, this taking a bornological vector space or a bornological algebra and equipping it with the pre-compact bornology is the same thing as the rigidification of some underlying category you can associate to the algebra. Okay, but this part is still work in progress. Yeah, so with this, I'll end the talk.
Okay, thank you very much, Dev, for a very nice talk. I wanted to ask, so you began emphasizing a lot that HL is invariant under passage to smooth algebras, blah, blah, blah.
Right,
But
right.
then when you talk about this reach,
Yes.
you did, and the right way of defining Kn, you didn't take this up again. So is Kn invariant under passage to smooth algebras, to dagger algebras?
This is I'm still thinking about this, but it's when you work categorically, you need to specify which category you're working with. So if you just take the derived category of the dagger algebra, then you've already kind of smoothened out, or you've already passed to a smooth subalgebra. There is no, at least at the moment, I don't know of a way to just take a category and define a smooth or an analog of a smooth subalgebra for a category.
Mm-hmm.
So, I mean, yeah, maybe let me write down what I said. So, ring theoretically, if you start with a bornological algebra, you can take its dagger completion. And then you can talk about whether your invariants, let's say, or another thing you could do is pass to the p-adic completion, and you can ask whether your invariant satisfies this.
Mm-hmm.
But if you pass to a category, then, well, you can ask what happens here. That is, if you do this or you do this. Now, by this work in progress that I'm mentioning, this is D of the pre-compact bornology applied to, well, wait. Give me a second to think. Yeah, so the smooth subalgebra is a purely algebraic phenomenon. This will not show up in the category. It's only this compactification that I have a categorification of.
Mm-hmm. And
so yeah, in general, you just have a functor from here to here, and it's probably not going to be the case that Kn of R dagger is Kn of R hat, because the proofs in local cyclic homology use homotopy invariance.
mm-hmm.
And this, yeah, this shouldn't satisfy this. Yeah.
Okay. And the other question is, in this context, I suppose you can consider a category of correspondences when you have, say, two algebras or two schemes or whatever.
Mhm.
And well, take your ridge construction applied to these correspondences and
Yeah.
take the theory of that, and this will give you a invariant theory. That's
Okay. Well, so
this.
okay, so you start with
Realistic property.
correspondence by category of what? Is it the like rings or C-star algebras?
Whichever you like. I mean, so I was more thinking of bornological algebras in the p-adic setting, but you may choose whichever.
Yeah, yeah. Okay, so you take bornological algebras in the p-adic setting. The one morphisms are these correspondences, and then there are two morphisms which are maps between bimodules, let's say. And now if you, okay, so this rigidification construction at the moment, I can only make sense of this in for one categories. There's no two categorical way to make sense of this. I think another interesting question which I had, which is related to what you're asking, is if you take just KK, let's say the C star or the complex KK, what happens if you rigidify KK? So this is related to James Gabe's talk. So he defined some KK nuke where he tampered a bit with the morphisms in KK. I'm wondering whether the rigidification of KK gives you something related to this. Because I think at some point in the discussion, the question arose whether this KK nuke, in his sense, has any universal property. If it is the rigidification of KK, then it does. It's the universal way to ensure that your maps are trace class.
Mhm. One more thing. You emphasize the fact that you don't want your Kn to be homotopy invariant, right? Now,
Yeah.
if you force homotopy invariant on it, do you
Yeah.
get your old Kn?
I think so, yes. Yeah. It would depend on which homotopy, but if you take the dagger homotopies, then I think this will give Kn.
Okay, so I'm done with my questions. Are there any further questions from the audience? I don't see anything in the chat. Nobody's raising their hands, so I will stop the recording here.